Hi, in this lecture we're going to talk about momentum and impulse. So often it is very possible that you have heard this statement being made on the TV or the radio station when an accident takes place on the highway or anywhere, to be fair. The statement reads, "The momentum of the truck crushed the smaller vehicle when they collided at high speed." So three words are colored: momentum, collided, and speed. I've colored these words to indicate that there is a connection between all these three things, right? And also what I have not colored is a smaller vehicle and a truck. So truck is obviously a big thing, a smaller vehicle is obviously a small thing. So what this essentially means is that there is a connection between the momentum of an object and its size, the speed at which it is moving, and when two objects of different sizes collide, then there is something happening which is related to whatever this momentum may be. Now our job first of all is to establish a definition of what momentum really is in physics, because whatever word you use in describing this real life situation, there is a very high possibility that physics is involved. So let's start by trying to establish a physics definition of momentum. How do we start to do that? Well, first of all, let's take a trip down memory lane and think about what we have done in the last chapter. We investigated work and energy. Work was the effect of a force being applied to an object for a period or for some distance. All right, so you make an object move by applying a force on it and make it move a distance. The connection between force and distance was what we defined to be work. Now we also mentioned something about force being applied over a period of time. That is what we will start with. We start by considering the effect of applying a force over some time. Why? Because as you can see from just this statement, momentum must be connected to the force, because two things are colliding, two things are physically coming into contact, so there must be a force that is acting between them. So force must be connected, and since speeds are involved, time must also be connected to whatever momentum may be. So let's go ahead and start with our second law of motion, or Newton's second law. This tells us that summation of all the forces on an object is equal to ma. We know that a and f are vectors. This is a vector equation, and summation of f can be written as just f net, the net force on an object, right? Now we want to find or investigate the effect of applying a force, a net force, on something for a period of time. To establish this connection, let us multiply delta t, a change in time, to both sides of this equation. Delta t here, multiply. Alright, so what do we have now? We have f net times delta t is equal to ma delta t. Now we also know the definition for constant or average acceleration was a equal the change in velocity over change in time. So change in velocity was vf minus vi over change in time, delta t. Therefore we have f net times delta t equal m. So wherever you see a, just replace it with vf minus vi over delta t. Vf minus vi over delta t times this delta t is there from before. What happens is this delta t cancels this delta t out, and we end up with f net times delta t equal to m times vf minus vi, right? Also these are vectors, so let's not forget about that. Right? Now we can see that whenever we have a subtraction between similar quantities at different times, so one is initial, one is final, we know that this indicates a change. So since it is the subtraction of a final velocity from an initial velocity, we know that this is just a change in velocity. So we can simplify our equation and write it as F net times delta t equal to m times delta v, right? So just a change in velocity. Now what is this product of force and time? We know that the product of force and a distance turned out to be work. What is the product of force with time? The net force times the change in time on an object is defined as the quantity known as impulse. And this is the left hand side of this equation. Now what is the right hand side? What does the product of mass and change in velocity signify? This is what we call change in momentum. Why is this a change in momentum and not just momentum? Because the velocity is changing from a final point and an initial point. So this is what we call a change in momentum. Hence we can simply define impulse to be denoted by I vector equal to, impulse is a net impulse, equal to the net force or all of the summation of external forces acting on the object, F net times delta t will give you what is known as impulse. And since the impulse is a product of force with time, the SI unit of impulse is just newtons times seconds. Alright, since this is a change in momentum, what happens when we don't have this change in velocity? We can just define momentum as, we denote it to be with a small p with an arrow up top because it is a vector, p equal to the mass of the object m times the velocity of the object at any point. This is what momentum is. When the velocity is changing between 2 points, we just get the change in momentum. Momentum is the product of mass with the velocity of the object. So the SI unit is equal to kilogram times meters per second. As you can see from this equation, impulse is equal to the change in momentum. So a change in momentum is the same as impulse. Alright, so if you replace momentum with a change, when there is a change in velocity, you get a change in momentum. Change in momentum is the same as impulse. Since these two are basically very closely related similar quantities, momentum and impulse, their units, because of this equal sign right here, because basically they're two different names given to very closely related quantities, the units Newton second is the same as kilogram meters per second. Alright, so the unit of impulse is the same as the unit for momentum. Therefore, the effect of applying a net force, a resultant force, over a period of time on an object gives me the impulse, the product of force, the net force with time. And that is the same as a change in momentum for that object. Momentum, as we have defined, is just the product of mass with the velocity of the particular object. Since these two quantities are very closely related and a change in one is equal to a resultant of the other, this is quite similar to what we investigated in the last chapter, the relationship between work and energy. Hence, we can set up an equation that we did previously. Previously, we set up an equation relating kinetic energy and the net work done on an object when a force is applied to move an object for a certain distance. We knew that Ki, the initial kinetic energy I start with, plus the net work, which is the energy I put in a system or I take out of the system, was equal to the final kinetic energy, the kinetic energy I ended up with. We can write down a similar equation for impulse and change in momentum by following from here. I net is just P final, the momentum final, minus momentum initial. If you bring Pi on this side, the initial momentum, then we are ending up with an equation which looks like this. Pi plus net impulse is equal to Pf. The momentum I start with, added to whatever momentum I put in or take out of the system, that is equal to the momentum I finish with. So this is somewhat similar to the conservation of energy principle. So here, if you did not have any work done by external forces, then you wouldn't have any net work. So that would mean kinetic energy initial would be equal to kinetic energy final. In this case, if I don't put in any momentum or take any momentum out, meaning that I am not changing my momentum, then the initial momentum would be equal to the final momentum. So this is an indication towards a conservation law for momentum, like we saw for energy, but we will meet that a little bit later. For now, let's test our understanding with an example. Alright, so here we have a man who falls out of a window which is 9 meters above ground level, let's say. He lands on his rear and it takes 0.35 seconds after he has hit the ground for him to come to rest completely. Human bones break for a compressive force greater than 850 newtons. We want to investigate if his mass is 80 kilograms, are his bones in danger of breaking? Alright, so let's see how we do that. So as always, let us start with a free body diagram when he first falls out of the window. Let's choose our axis, y-axis, as upward to be positive, just cause it doesn't matter if you choose downward. So he has a weight which is the mass times g, mass is 80, and no air resistance, so we have no other forces acting on him. What are the variables that we know? We know that initially the velocity must be 0 since he's falling out of a window. When you fall or when something is dropped, initial speed or initial velocity is 0. He's falling under gravity, which means near the surface of the earth, acceleration is negative 9.8 meters per second squared. And he falls a displacement of 9 meters, so 9 meters downwards, that's a y, it is negative 9 meters displacement. And we don't know anything else about this motion until he reaches the ground. Alright, so he reaches the ground at some speed, Vf, which we don't know. Okay, we don't know what is the speed at which he hits the ground. Now, this situation was just before he hits the ground, just before he physically reaches the ground. What happens after he reaches the ground? Let's start with the free body diagram in red, which is the free body diagram for when he is in contact with the ground. So on the ground, this is the guy. His weight will be constant at 80 times g, it doesn't change, and there will be a normal force exerted by the ground on him because they are physically in contact. This normal force acts on this guy for 0.35 seconds before he fully comes to rest. So after reaching the ground with this velocity Vf, he will take another 0.35 seconds during which he is in contact with the ground to finally come to rest. Since this time frame is given for which a force acts on an object, namely these two forces are acting on the person for this amount of time, we immediately think about what we just learned about impulse and momentum. Whenever there is a force being applied over a period of time, whenever there is a net force being applied over a period of time, there is a change in momentum. And this net force over a period of time is my impulse. How do we know that there is a net force in this situation? Well, since he reaches the ground with some velocity Vf, he takes another 0.35 seconds before he completely comes to rest. Therefore, this velocity, which was not zero, reduced to zero in 0.35 seconds. So the velocity changed during this time, which means there was an acceleration. Whenever there is an acceleration, there is a net force acting on the object. So there is a net force acting on this man when he's touching the ground for 0.35 seconds. After 0.35 seconds, there is no more net force. So what is the net force? The net force is just, if upward is positive, sum the forces on it. N is a positive force minus the weight, 80 times g. This is the net force, N minus 80 times g. This is the net force acting on the person for 0.35 seconds. Therefore, what does this equation become? It becomes F net times delta t equal to mvf minus mvi. What is Vf? Vf is when the person fully comes to rest after touching the ground. So this is 0. What is Vi? Vi is the speed at which the person just reached the ground. So the velocity final here is the initial velocity when he is touching the ground already. So let's just call it V to avoid confusion. And remember that this is V, and we have to find what this V is to proceed with this equation in order to find what this normal force is. Is it greater than 850 or less than 850? We have to investigate for the guy to be in danger of breaking his bones. Alright, so how would you proceed to find V? You have enough information to set up a kinematic equation, but whenever possible, I like to work with vectors. I like to work with scalars because vectors involve signs, and sign changes often confuse me. How do we use scalars then? We can use our work energy theorem. Pretty simple, and it is often more simpler than using kinematics. Work energy theorem tells me that Ki plus Ui plus work non-conservative is equal to Kf plus Uf. There is no non-conservative work since there is no air friction or air resistance, so we can just set that to 0. What is Ki? Ki is when he starts off here, Initially his speed is 0. We know that K is equal to 1/2 mv squared. If speed is 0, this is also 0. Ki is 0. What is Ui? U is the potential energy. It is the summation of gravitational potential energy plus spring potential energy. There are no springs involved, so we can just set that to 0. We only have gravitational potential energy. What is gravitational potential energy? This is equal to mass times g times the height or the y displacement. He started off here. This is his initial position. So initially his kinetic energy is 0. There has to be some potential energy, because we know that energy can only be transformed and transferred. It cannot start from 0 altogether. So if it didn't have a kinetic energy at the beginning, it must have some potential energy at the beginning, and vice versa. So what is its potential energy? The guy was up there, so 80 was his mass times g, gravity, and he was displaced, or he was at a height of 9 meters above ground. So h was 9. This is equal to Kf. What is Kf? Kf is 1/2 m Vf squared. What is what we are trying to find? We have given the name V. 1/2 m V squared, the speed at which he just reaches the ground. All right, and then plus Uf. Ground means this is y equals 0. If y equals 0, then there is no height from the ground. So potential energy final is 0. So we have this equation: 80 times 9.8 times 9 equal to 1/2 mass is 80 times V squared. 80 is on both terms, so it can just go away. And then we multiply 2 to both sides of the equation. We have 2 times 9.8 times 9. You can square root both sides, so you have square root here and then square root of v squared, which is just v. This comes out to be v equal 13.3 meters per second. This is the speed at which the person reaches the ground. Alright, now we are free to go ahead and use this equation right here. So let's go ahead and do that. What is F net? F net is, remember, n minus 80 times g. N minus 80 g times delta t. What is delta t? 0.35 seconds. 0.35 seconds. MVF is 0 minus MVI. MVI was just negative 13.3. Negative, and so minus M is 80 times VI. Now remember that he was falling down, so his velocity of hitting the ground was pointing in the negative y direction. We chose upward to be positive. So this V is actually, and in here we calculated the positive because energy is a scalar. So energy has a speed in this formula. This is the speed, not the velocity. So anyways, this velocity will have a negative sign up front, negative 13.3, because it was pointing down. If you then rearrange the equation, we have n times 0.35, 0.35 times n minus 80 times 9.8 times 0.35. This is equal to negative 80 times negative 13.3, such that 0.35 times n is equal to 80 times 9.8 times 0.35. We just took this on the other side, minus, this was already here, 80 times minus 13.3. If you go ahead and divide both sides by 0.35 after carrying out the subtraction, we have n to be 3,824 newtons. This is way bigger than 850 newtons. So yes, if he falls at a speed of 13.3 meters per second from this height near the surface of the earth, then he's at tremendous risk